Hey everyone, my name is Brian Jeffcoat, and today I'm going to be talking to you all about global positioning system. I'm going to start off with what a global positioning system is, and then move into some of the preceding technology and the history that led up to today's global positioning system. And later on, we'll get into how they work and how they're applied in civilian and military uses. So, what is a global positioning system? Well, by definition, it is simply a system that uses different signals to get an accurate location reading of an appropriate receiver. Thanks to today's technology, this is all done by satellites, and different examples can be seen by the picture on the right. The GPS is the global position system used by the United States government. Galileo is used by the European Union. GLONASS is used by Russia, and COMPASS is used by China. So, how did we get to today's different global positioning system units? Well, these are examples of hyperbolic radio navigation systems. These were two systems used during World War II, usually for naval forces. And it should be noted that these are not global positioning systems. They didn't cover the entire globe, but they were the first technology we had of getting accurate locations. Now, the way these worked was they had to have local radio stations with known locations keeping track of the time. These radio stations would constantly send out signals, and then these, on, like I said, submarines or ships, they would get those signals, they would take the unit's current time, subtract the time the signal was sent, multiply it by the known speed of the wave, and that would give you the distance between you and that radio station. Once you had the distance between you and 3 local radio stations, you could use triangulation to pinpoint your location. Now, this was very accurate, but like I said, it wasn't a global system. And governments didn't want to dot the map with these radio towers all over the place just so we could get accurate locations. So what was the next step of the process? Well, the first actual global positioning system was the transit satellite system. Now, in 1957, when Russia sent Sputnik up into the orbit, 2 physicists, William Guire and George Wyffenbach, working at the Johns Hopkins Applied Physics Lab, decided that they wanted to study the radio waves being sent out by Sputnik. After only a few hours of looking at the waves sent out by Sputnik, they realized that they could apply the Doppler effect to figure out where Sputnik was in space. Now, I'm not going to get too deep into it, but the Doppler effect is simply a set of principles that describe how waves being emitted by moving objects work. So they theorized that if they had their own satellite in orbit and they knew its position at each and every time, they could use the inverse of the Doppler effect and get the position of a receiver on Earth. In 1958, the project was started, and as you see in the picture in 1959 on the left, this is a picture of Transit 1A. It was the first prototype. It was launched into space, but it failed to reach orbit. But in 1960, the Transit 2B was sent and successfully placed in orbit. After a few months of testing, as theorized, they could get a very accurate location. So over the next 4 years, 7 more satellites were sent into orbit, and by 1964, the U.S. Navy started using the transit system to get their locations for different naval systems, and it covered the whole globe. Now, what were some of the drawbacks to this system? Well, due to the lack of computing power and the lack of actual satellites in orbit, the transit system could only give you an accurate reading about once per hour. So this was great to keep, tabs on where submarines were, but as we move into later, more advanced missile technologies and so on and so forth, it just wasn't going to cut it. Also, different solar flares and magnetic storms in the ionosphere of Earth could greatly decrease the accuracy of the transit system. So, what do we do to accommodate it? After the transit system, starting in the early 70s, was the Omega system. The Omega system is basically just a very large form of the earlier seen LORAN and DECA systems. Thanks to increase in radio technology between World War II and the 70s, we were able to send waves much farther. So the Omega system covered the entire globe with only 8 radio towers. This picture on the left shows one of these radio towers in Haiku, Hawaii in 1971. So they worked basically like the DECA system. Each radio tower had an atomic clock on site, and an atomic clock is just a clock that slows down different elements and analyzes the speed of their electrons to give us the most accurate time. These clocks were accurate to 100 nanoseconds. So these stations would constantly send out their time, and it would apply the same thing. The people using the Omega system, they would get that time, take the current time, subtract it, multiply it by the known speed of the waves, and they would get their distance. But unlike the DECA system, you could never be in contact with more than 2 Omega stations at once just because they were spread out so far. So this would produce 2 circles in which you could be intersected at 2 points. And a technique known as dead reckoning in navigation was used to define which point you were at. Dead reckoning basically says that one of the points is going to be impossible. It'll put you way up in the air, underground. So it was pretty easy to determine which of these positions we're at. And what was the drawback of the Omega system? As you look on the right, the Omega system was very inaccurate. It could get you off by about 2.2 kilometers. The transit system was farther down there with only 400 meters, but like I said, it could only be used once per hour. So from 1970 to 1997, these two systems were used in a combination to give an okay global positioning system. They were the most efficient global positioning system until today's GPS, which was put in effect in 1997. So how did we move to the new GPS system? Well, different parts of the government argued that they needed a more efficient GPS system. The lack of reliability of the transit system and the inaccuracy of the Omega system simply wasn't going to cut it for new technologies being made on Earth. But the government did not want to sink in the billions of dollars that would be needed for technology, research, development, all that until the Cold War. It was argued in the Cold War that the only viable defense we had against a nuclear threat was our Navy's submarine ballistic systems, ballistic missile systems. If a nuclear missile was shot at us, it was designed that we would shoot the missile out of the sky. One of the very important data points that these ballistic missiles needed was their current position. They had to know their current position so they could be shot at the correct angle and so on and so forth to hit incoming missiles. Now, as being 2.2 kilometers off, we would obviously miss that missile, and if there was an electric storm, the transit system wouldn't work. So, for national security, in 1973, it was decided by the Pentagon to look for and implement a new GPS system. So, these three men are known as the fathers of the modern GPS system. Going from left to right, they are Roger Easton, Bradford Parkinson, and Ivan Gidding. And these are the three main inventors and designers of today's GPS system. A lot of the credit goes to Roger Easton, as he's the theoretical physicist that devised how we should put the satellites into orbit and how they could stay in orbit and so on and so forth. And after 15 years, in 1989, the first satellite of the modern GPS system was put into orbit, and by 1994, the 24th satellite was placed and completed the circuit covering the globe. 8 satellites have since been added, but it was still fully functional back then. So how does today's GPS system work? Well, if you look at this animated picture on the left, it shows that given this point on Earth, it shows the Earth rotating and the satellites moving around it, and how many satellites at that point you are in contact with. For today's GPS system to work, you have to be in contact with at least 4 satellites. And this just means that the Earth cannot be in between you and the satellite of 4 satellites. So what do these satellites actually do? When you want to know your position using GPS, the only things that these satellites send you is 1, their location in space, and 2, their time. Each of these satellites has on board 4 rubidium atomic clocks, which are accurate to 50 nanoseconds. This time, it has to be altered a little bit because due to Einstein's theory of special relativity, time passes differently for the satellites, but once it's sent to the GPS receiver and altered, the same process is applied just like in the radio signals. The receiver's current time is taken from the time the satellite sent its signal, that is multiplied by the known speed of the signal. That gives you the distance between you and the satellite. Once you have the distance between you and the satellite's position in space, you can use a geometrical process called triliteration. Now this is an example of triliteration with GPS. This basically says that when you have a 3-dimensional space and you know the distance and position of something, it provides a 3-dimensional sphere in which you can be, unlike the 2-dimensional circle with the on-planet radio system seen earlier. So as you can see with one satellite, it can put you anywhere in that sphere, obviously very inaccurate because you're probably not on the moon. With the second sphere, it puts you somewhere in a 3-dimensional cylinder shape. With the third sphere, it puts us in 2 points, and finally with the fourth sphere, it all intersects in one singular point. Now with today's computing power, it doesn't take any time at all for the GPS to give you your exact point. It's a simple subtraction, multiplication, and the math behind triliteration is pretty simple. So that's how we get today's GPS system such quick results and such accurate results. If you remember the chart earlier, it said today's GPS system is at all times at least accurate to 9 meters. So what do we use today's GPS system for? Well, I'm sure everyone in this room has sometimes used an onboard GPS system, maybe a TomTom or something on their phone, to get turn-by-turn directions. This is a great example of how accurate and quick the results are given. If they weren't given quickly, the nice lady would tell you to take a right 10 miles back. So obviously they can keep track of where you are at all times in real time. And it should also be noted that these don't use cell phone service. You don't have to have like your cell phone service to be able to use the GPS system because it contacts directly with the satellite. So this is examples of GPS. So what else do we use it for? Well, a lot of people don't know that since we have these GPS systems floating around with such accurate clocks, the world clocks are synchronized to them. Like I said earlier, they're accurate to 50 nanoseconds, which averages out to be about, they'll be wrong by 1 second in about 30 million years. So for now, it's pretty okay to use. All cell phone carriers such as Verizon, Altel, and Samsung, their networks run off these clocks. That's how everyone's phone is always synchronized. You know, the minutes will change at the exact same time. That's because they all run off the GPS system. Here's a man who was trying to get his accurate latitude, longitude, and altitude positions, which could be done previously, but the GPS system makes it a lot easier. This could be used for a lot of things, such as laying down property lines, benchmarks, noting how tall a building is, so on and so forth. All very practical uses. It should also be noted that thanks to Bill Clinton in May 2000 is when civilians got complete access to GPS. You could buy a GPS system prior to that year, but it had select availability, which basically said if you were in the military, we gave you kind of like, it could tell you that you were 5 meters from this point, but the actual signal told you were about 100 meters because they didn't want it to be used for weapons. But Bill Clinton decided that it wasn't going to be used as a threat to us, and civilians needed it, so in May of 2000, select availability was shut off forever. So what does the military use GPS for? Obviously, they had to get some great benefits because they're the ones that spent the billions of dollars. It should be noted that any GPS that works at speeds greater than 5,000 meters per second or at speeds higher than 10,000 meters is considered a weapon by the U.S. government. This is why we saw different examples of the satellite systems for different countries because they didn't want other countries to get ahead of them in a military sense. And this is pretty, no one complains about this because why would a civilian ever need to know where they were in a fighter jet? So examples of how the military uses GPS are, like you see on the left, it's an unmanned recon plane. Now these recon planes, they have to know exactly where they are, exactly where they're going, which direction, what speed, and what's around them, or else they might just run into a mountain, which is not the desired thing. So this GPS system, earlier I talked about how the GPS system is accurate to 9 meters. With higher processing power, such as the things that will be put in these, it's accurate to about 2 centimeters. So it can really keep track of where you are. Other examples would be in the top right. This is a laser-guided missile system. These missiles work by being shot up in the air. When they reach their max altitude, GPS determines where they are, where they need to land, and the missile affects its trajectory accordingly. Other examples would be, this is a prototype for the Mars Land Rover. It was tested by using GPS to move it around at a certain angles through the desert. And granted, our GPS system wouldn't be used to move the actual Mars Land Rover, but the satellite technology is quite similar. So to recap, I think it's just amazing to see how in a simple 60 years we went from giant bulky systems that needed radio beacons all over the map just to get somewhat accurate results to a global satellite system that at any time of day, no matter what's going on in space, magnet storms, solar flares, anything, I can get the exact time, position, altitude, speed of my receiver, which comes, you can go buy an onboard receiver for $30 nowadays, and it's all updated, and it just happens so quickly. And it's hard to think of ways to improve today's GPS system. A lot of money was put into this new system, and it certainly worked because we get it in real time, we get it accurate. There's no other way to do it.